Okay, hello everyone. So for the last lecture of EEE 105, let's talk about communication interfaces. So why do we need communication interfaces? Well, let's say for example, let's create, for example, the simplest way that we could interact with a joystick, for example, from our created microprocessor. So let's say we connected these two with some sort of uh, data line that is say 32 bits in parallel, and let's say that means we're done. So what will happen is the microprocessor tries to send data, and then it tries to send a 101010 stuff, and it tries to give that to the joystick. The problem with this is that in reality what the joystick will see is that and then nothing. And the reason for this is one, the device may not have a clock at all, or two, the device will have a much slower clock than the processor. So let's say, for example, that your processor was running a clock at 2 gigahertz, and your joystick, if it, well, I don't think it needs an internal clock except for communication, but say it was running at 2 kilohertz. Now, for the joystick, the microprocessor might as well be flash and is running at, well, actually a million times faster than the joystick itself. So, what would happen is that in the time that it takes for the joystick to try to read one bit, um, the microprocessor will have sent like a million bits. So, what happens here is that it looks like a spike, the joystick, and the joystick will not be able to understand the information that the microprocessor has sent. So what they need to agree on is uh, how fast the communication will be. So then we add a clock line to the communication, and then the joystick will understand what the microprocessor is saying. Now the problem with this is, say for example, the connection has been idle for a while, and then all of a sudden it jumps, and the joystick is like, "Oh, wait, we're communicating. I didn't know we were communicating," and so it gets surprised that the microprocessor is actually sending something, and so it starts noting it down. But what it notes down is like 101100 or something like that, and then um, so the joystick is like, okay, I'm now writing things down, but when do I stop? Like, are you not sending anything, or are you sending me zeros? And that's a problem. We need, like, the joystick doesn't know when to stop receiving the bits, and so that necessitates, say, okay. So first we needed the clock, and two, we needed a stop bit. We need to know when to stop. And the thing is, okay, even if it knew when to stop, say for example, okay, it knew to stop at 8 bytes, at 1 byte of communicated data. So it knows that the microprocessor was probably trying to send a 1011 000. But that's not what the microprocessor was actually trying to say. It was actually trying to send 01011 and then three zeros. And that's a problem because the joystick, because the microprocessor didn't tell the joystick when it was starting. It thought that the first bit was a 1 instead of a 0. And so what happens is that we also need to decide in our communication interface protocol when the communication should start. So we have to decide when a communication starts and when a communication ends. So uh, that's one other thing that we need to decide on. And actually, we don't really need another line of data to do that. We just have to decide on a standard and agree upon that, and have the devices agree upon that standard. That's why we have the USB standard, or the I2C standard, or the SPI standard. So yeah, those two are absolutely necessary, and that's why we need communication interfaces. And let's see here. So there are two types of communication interfaces. There's a parallel interface and a serial interface. Now, one could see the parallel interface sends an entire 8 bits of data over one one clock cycle. It just sends them all at once, and the receiver receives them all at once. And that's pretty good. As compared to a serial interface where all of the bits have to be sent over one wire, it is literally quite literally 8 times slower than the parallel interface, because the parallel interface sent 8 bits at once. So what would why would we ever choose the serial interface? Well, the thing about that is it costs a lot to add extra pins on your chip. Like for example, over here for your PIC 24 FJ64G A002. So Koi 115 used to use GB002. So this is just like a very related microcontroller. You can see here that all the R somethings are actually GPIO pins. So you can configure these to be able to send or receive 1/0 as digital input bytes to your program. And the thing is, no matter how many these are, they are still less than 32 pins. But what if, for example, you wanted to send 32-bit data? You are always limited by what your hardware is giving if you're using a parallel communication protocol. And as I've said, it costs a lot to add an extra pin to your microprocessor or your microcontroller, because in reality the processor inside this thing is that small, and most of this thing is actually that it's actually the metal connecting to it. And so the thing becomes much bulkier as you add more and more more and more pins. So it actually costs a lot to interface to add more pins to your chip. And so what do we do? We choose serial communication protocol. We can send as many bits as we want. Just we just have to decide on the protocol over one wire, and that's why uh, serial communication protocols are heavily favored nowadays. So the USB is the universal serial bus. It is serial. Um, and the SATA, which we used to use, we no longer use it anymore. It's not heavily used anymore, is what I mean. But it stands for Serial ATA, so it's a serial communication protocol as well. So most of the things that we use today are serial communication protocols. So let's talk about one type of protocol that would be simple to start with. It uses two wires. It's called the TX and an RX. That is the transmission wire and the receiver wire. And so this is for transmission, and this is for reception. And what happens here is that whenever we want to, whenever a communication takes place between two devices, let's say this, there were, well, actually, this is these are the two devices now. We have DTE and DCE. The thing is, the the communication starts by deciding on a start bit, which actually solves one of the communication problems already. We have a start bit, so the receiver knows when to start listing down the information, and then after the start bit, the UART protocol decides on a number of bits. It has a number of bits to send, and then it also has a stop bit for good measure. So the start and stop bits have to be decided on by the participants. The number of the byte length to be communicated over is actually variable depending on the agreed upon stop bit. Actually, the stop bit doesn't not even have to be just a bit. It can be like more than one bit, but the stop there is a certain pattern there is a certain pattern of sent bits that UART can use to decide whether or not the communication is over. And we still have one more problem, that is what if they're expecting different transmission rates for the bits. Well, that is solved by not sending over a clock, not by sending over a specific clock, but rather by deciding the clock beforehand on the standard. So this is called the baud rate, and what it does is that the baud rate decides how much time, how much yeah, how much time it takes for one bit to be sent. So this is a baud rate of 9600, which is fairly common. And what happens here is that every bit is expected to take nine every bit is expected to take 1 over the baud rate seconds to send. So how does the receiver take advantage of this? Well, let's see. So for a single UART communication to take place, the receiver waits for the start bit. Usually, that is when the idle state, that is VDD, it goes down to 0. So then that signifies the start. Now from the start, it counts half the baud rate. So here's the start. It counts half the baud rate, and then that's where it starts, and then it counts one of the baud rate, and it ends up in the middle of bit 0. Whatever the voltage is on that on the transmission line at bit 0, it lists down as the value, and then it counts another baud rate time, and then it gets the value in the middle of bit 1, and so on and so forth, until such time that the stop sequence is encountered, or the number of bits that they agreed upon to send is already has already been sent. So yeah, that's basically how the UART uh, the UART functions. And this is the fact that the name contains asynchronous, because they don't have to agree upon a clock. They don't have to share a clock. They don't have to handshake a specific clock for the protocol. All they need to do is to send the bits within agreed upon baud rate by the designer. That means that you cannot use UART devices with different baud rates unless you configure them yourself, which means that you have to interfere with some sort of configuration inside the device. So, UART also solves some of the multiple peripheral problems that we have. So, a single UART interface actually, if you saw in the last lecture, we had the table where memory mapped I/O was mapped to, say, for example, a UART interface, and that UART interface can be used to interface with a lot of UART devices. So, how does that work? Um, what happens is that you use two different communications of sets of like communication packets to interface with more than just one device. So say for example that your microprocessor was master one. Well, what happens here is that the master one, in order to communicate with, for example, slave two, it first sends the address of slave 2. So then, if, for example, the SDA was deasserted, so it was deasserted suddenly, so everyone starts listening because that's the start bit. So then everyone starts listing down the address bit. But then when the address bit is completely sent, um, what happens once the address bit is completely sent is everyone compares that with their own address. Like everyone has their own address, you assign it to them, and if their address is correct, then uh, the the uh, the the address that was the address that was the address that was broadcasted by the master is accepted by that specific slave, and it has to send a specific acknowledge bit that is apparently a 1 in this position, indicates that the address slave is not was not able to respond to the request, which means that there was the slave was probably missing. But after the slave knows that it is the slave that is being communicated to, then it is the only one that listens to the next few bits. We can see here there's a lag in the communication that is an idle time, and then this is another start bit. And then the slave listens to slave 2, for example, listens to the communication of master 1. None of the other slaves, well, master 2 can also receive, but none of the other slaves need to be listening anymore, because it is not the one being addressed to. And that is how you are able to communicate with multiple peripherals with one wire, using, well, with two wires using the UART protocol. But for some UART protocols as well, the start and stop agreements actually happen, not necessarily due to just the existence of a start or a stop bit. It can be a pattern of events. So, for example, here, the start condition for this specific UART protocol is that the SDA, or the TX goes low before the SCL goes low, and so that becomes the start condition. And then for every cycle after that, the SCL has to go low before the SDA. Now, what happens is, if the SCL goes high before the SDA, then that means the communication stops. This is also a stop condition, if you can see. So that's it for UART. Let's discuss the other communication interface that we will be discussing for this lecture, which is the serial peripheral interface. The serial peripheral interface has a clock that is SCK. It has a clock that is distributing for uh, for all the peripherals. Um, So SCK actually stands for serial clock. What happens here is that depending on the devices listening do not have to agree upon a specific baud rate beforehand. The serial clock is the one that determines how fast the bits are sent. And whenever the clock goes high, for example, or something, any signal depending uh, on the status of the serial clock, it becomes the factor for the communication. So, for example, master out, slave in. That's what MOSI means for. So, let's write that down here. So the MOSI wire is reserved for the master to drive, and the slave to receive communications upon. Now the MISO wire is where the slave drives and the master reads. And so what happens is that, referencing the serial clock, the reader reads whatever the bit is on the current whatever the bit is at the time that the positive edge of the serial clock happens, which is right in the middle. That's why it happens right in the middle. Now, there is an optional wire to be used, that is the communication enable. If the communication enable in this case is asserted, that is, it's negative, is deasserted, um, the communication can take place. But if, for example, if it wasn't asserted, then the communication will not take place, regardless of whether or not the serial clock is ticking. And why would this be useful? Well, if, for example, you have multiple slaves for your master microprocessor. So if, for example, your microprocessor was connected in using these three wires to multiple peripherals, then if you don't have the communication enable wire, then all of these guys will be listening to whatever you say, and some of them might be different devices, so they would be listening to the wrong commands. And if, for example, you also connect the master in slave out of all of them to your microprocessor, then all of them would be driving at the same time, which is pretty bad unless, say, for example, you use a multiplexer. um, so this is the yeah, you multiplex the multiple MISO signals and put them back into the microprocessor. So it doesn't really matter for the uh, for the for the signals going back, but let's say it probably matters if you're trying to configure the devices and everyone starts getting the same configurations. Uh, so as a sample of say a slave circuitry for SPI, we can see here. So basically what happens here is we take the MOSI, the master out slave in signal, and we add it to the 7 bits. This is how the communication takes place, because in this specific communication, the slave, okay, the master tries to send the data T to the slave, and the slave tries to send the data D to the master at the same time. Now, for every cycle, at first this the all the bits of D are here. It is placed into the 8-bit register, which is clocked by SCK. So if count is 0, 6 bits of the of D70 is placed into this wire here. So in the first cycles, you get 60 of D, and then the MOSI value for the last bit, which is T of 7. Yeah. So which is T7. And then what happens next is well, okay, what happens during the cycle as well is D7 is actually sent to MISO. So okay, what happens after that is in the next few cycles, this thing is connected back, and then its last bit is sent out. So what happens is now D6 is the last bit. So what gets sent out is D6, and now you only have D50, and now you have the T from 7 to 6 over here. And so as the cycles go on, at the end, what you will have in this as the output of Q is T from 7 to 0, and all of the D bits will have been sent. So this is just a really efficient way um, to implement an SPI slave circuit. It doesn't really have to it only has to use one register, which is really really nice considering that you're trying to work with two different sets of data at once. This is from the Harris and Harris book. Okay, so we won't be discussing any more protocols other than the UART and SPI in this lecture. I2C is relatively simple as well, at least as compared with all of the other protocols that are listed here. SATA is a protocol that is used for your hard disk devices or some of your other peripherals. PCIe was a communication. Not sure if it's still used, but it was the communication protocol for say GPUs or network interfaces. If, for example, you wanted like the old computers, they didn't have Wi-Fi adapters connected to their motherboard, so you used to have to buy I think Ethernet slash Wi-Fi network adapters to be connected to your motherboard, and the PCIe bus was a slot in the motherboard to be able to interface with that, and that's what PCIe is. SATA is for HDDs and SSDs. I2C is something that is very well used by hobbyists in microcontrollers. Well, not just hobbyists, it's just very well used by microcontrollers in general. It is also a serial interface, so which uses very very few which uses very very few wires for itself. For an explanation, or at least an overview of what the USB protocol would be like and and how it works, Ben Eater has a really good video on that where he demonstrates the how a USB keyboard works by showing the signals on an oscilloscope. So you can see here, you can see it actually happening. So that marks the end of Triple E 105. I will be releasing problem set 2 as soon as this lecture is out as well. And that will be due on January 6th, which is the end of the finals week. And so yeah, good luck everyone. And please submit your problem sets as soon as possible.